Okay, hello. Rebecca, you asked me to answer these few questions, and I'm going to do this one now, and hopefully, by the time I'm done with my presentation at my conference tomorrow, I'll have answered the second one. But both of those things should happen before 5, so before 5, you will know the answer to both of those questions, either through getting them from the test or getting them from me. So for this one at least, we're covering an ionic compound is electrolyzed with an 18 amp current for 2 hours. This deposits 39.55 grams of metal at the cathode. Is this compound COBr, COBr2, COBr3, or COBr4? This must be proved with calculations. Extra credit. Was this done with a molten sample or aqueous sample? Defend. Ooh. Defend. Weird verbiage. But I did some math here so I can get it out of the way. But first things first, they give us a time. We know this is electrolysis, and we know they give us a time, they give us a current. So we know that current is related to moles through this equation up here. Current is related through moles through charge. And charge is related to current through, I know it's a bit annoying like that, but through I and T. I being current, T being time. So in this case, down here you can see our 18 amps multiplied by the time in seconds, because amps is in seconds. Now, you may wonder, where is this coming from? This is Faraday's constant down here. This is an expansion of the second equation. So Faraday's constant, we want to find the number of moles first and foremost, because when you're in chemistry, you always want to find the number of moles. So I'm just going to do the math real quick though. 18 times 7,200, you should get something like 129,000 with like a 6, something like that. So that is the charge. Now that's fine and dandy. You have the charge, so you have Q now, but you need N. N is the number of moles. So we divide by Faraday's constant, which I have right under here. So if you follow this here, you should have the correct number of moles. So this so what I just calculated divided by everyone's favorite number, Faraday's constant, 96,485, and that gives us something like 1.334 moles, right? This is moles in total. Now, if you will give me 1 second, I needed to pause for a quick second. Now, this is moles of electrons, so I'm going to write of E minus of E minus. Now we know that we still have to find out which one of these compounds is it. So what we can do is we can write out their half reactions. CO plus CO, so this would be CO plus, and then E minus equals CO. This would be CO. I'm sorry if you don't like my writing. I'm writing with a mouse, and this is the best I can do. CO plus 2E minus equals CO, and so on and so forth. But I'm not going to write them all out. Now, one thing you will notice is if you look at this, only we can kind of eliminate 2 of these answers. First of all, this doesn't actually exist. There's no reduction potential for this compound, so we know that this ion probably doesn't exist, and the same thing for Br4. Well, that's not exactly true, but shoot. In what we're working with right now, there's not actually a standard reduction potential for these 2. They really don't wanna. These really have quite a bit of trouble. So we know off the bat that we can eliminate these outer 2, but now we need moles. We have moles, right? So we're given a mass. We know it's a pure compound because it's the metal. It's a plating of metal. When you plate metal, you get a pure metal. So you can use this over here, which this is the molar mass of cobalt, which is what we have here, CO, cobalt. If you look on your periodic table, you'll see it's 58.93. I know it's a really rough 58.93, divided by the mass that we get in the equation. This gives us a mass of 0.6, what is it? Let me do that again, 39.55 divided by 58.93. That gives us a mass of 0.671 moles of CO question mark. Now, we have moles of electrons. You see there's coefficients on each of these electrons. The easiest way to do this is we divide each of these. So this would have 1 electron, 2 electron, 3 electron, 4 electron. We divide this number of electrons by each of those coefficients to figure out which one it is. So we know it's not 1, so first of all we can guarantee cross off 1, because 1.34 divided by 1, which equals 1.34, is not 0.671. And if you do quick math, you can probably figure it's probably COBr2. So we'll just confirm 1.34 divided by 2. It is I got 0.67, so we know it's cobalt bromide 2, right? Now, they want to know whether this was a molten sample or an aqueous sample. Now, this depends on standard reduction potentials, so you can't actually do this with just math, right? So I can actually delete all this math, and you're probably happy to see it go. Who loves math? Who loves math, especially when it relates with chemistry? I know, nobody. But we're going to use more math, but it's just simple comparisons at this point. So we know it's CrBO2. COBr2. COBr2. Well, we can first look at melting points and tell that unless they said somewhere here, I don't think this is at 600 or something degrees. These are ionic salts, they normally melt 600, 900 degrees. So, is this a molten sample? We're not given a ton of indication for that. But it may still be true. We could be working with a molten salt, right? Now I'm going to pop over to my chemistry textbook and show you something here. With a pure molten salt, right, the way we can tell is when we're doing electrolysis, if the potential of water in an aqueous, if the potential of water is lower than the reduction potentials of the of the compound we want. So in this case, they're doing the electrolysis of sodium chloride, right? For sodium chloride, if the potential is lower, like here you can see H2O's potential is lower. That means this is more favored because of thermodynamics. This is more thermodynamically favored. So water is going to reduce rather than you getting the production of chlorine gas. And you can see the same thing on the metal. The metal has a really high, reduction potential. So it really doesn't want to be reduced into sodium metal. So we can see here that if you use aqueous sodium chloride, it's not possible to get the metal in chlorine gas. But if you look up here, we use molten sodium chloride. This is how you get the metal formation and gas. So molten is, you have to use molten if your reduction potentials are more negative in the case of cathode. So you see here, this is a greater negative value. This is less favored than this value for H2O. And you see here, this is a more positive value. This is less favored than this. So the smallest value is more favored. So if we look at our standard reduction potential table, right, which we can see here, and we look at cobalt, cobalt is down here. We have CO2. This is minus 0.28. We look back, our negative 0.28 is less than this, so it's favored over H2O, and the reason it's not H plus is because this is an acidic solution, so there's a low concentration of H plus. It's mostly pure water. But we can see that this is more favored, so this would be more favored, so we can use an aqueous solution. Now, if I remember correctly, I don't believe cobalt bromide is a basic salt. If I'm wrong there, but we will get cobalt formation in an aqueous solution. So we can tell here that this can take place in an aqueous sample, and since they don't give us any indication of high temperature, I'd pick the aqueous sample, and that's this question. If you have any questions, comment. I might have taken a bit longer than I needed to, so I hope you stuck with it the whole way through. And if you need any clarifications, again, comment.